Hey guys, welcome back to Get Smart with Rory, once again bringing you Last Week in Science. Y'all might notice things looking a little bit different this week. Well, I've been moving, so for the time being, this is our new studio. Anyway, plenty of news this week. Sure, I could talk about the discovery of an antibody which could be used to regrow teeth, or the naturally occurring protein, neuratin, which new research suggests could be used to suppress allergies and autoimmune disorders. Links in the description. But this is all medical science, which is 2 to 10 years from seeing anything like human trials. And this week was loaded with big news on space and physics. So that's where I want to put my energy. First, pure physics excitement. We have the first laser manipulation of antimatter to cool it to near absolute zero, which would be useful for then being able to further study properties of this really rare volatile substance. For people who don't know, antimatter is, well, matter, but then the opposite of that. It has mass, charge, spin, but if it comes into contact with regular matter, both are annihilated and turn into pure energy. Obviously, we don't just keep bunches of this laying around, but we've made a few nanograms worth in particle accelerators, and a bit is naturally continuously created through radioactive beta decay, also known as positron emission. A positron is literally an anti-electron. Anyway, new antimatter research is always going to excite me. Researcher Makoto Fujiwara, who was the first proponent of the idea of laser-cooled antimatter, says his next dream is to create a fountain of antiparticles by launching cooled antimatter into free space, which he claims would enable entire new classes of quantum measurements which were previously unthinkable. Then, as I said, we also have some big space news. First, the discovery of what is being called the Goldilocks black hole. A few weeks ago, I discussed the discovery of a supermassive black hole at the center of a quasar, and how its size and age called into question our theories surrounding the formation of supermassive black holes. Well, one problem astronomers have had is that black holes seem to come in either one of two size ranges. Either the run-of-the-mill common black holes created by the death of a star, and supermassive black holes, which are found at the center of most, if not all, galaxies. But we don't have many black holes that are in the middling size range. Of course, finding any new black hole can be damnably difficult. By their nature, they don't give off any light of their own, so if they aren't actively eating a star or something, we have to resort to watching for their pull on the orbits of nearby stars or gravitational lensing. And that's exactly how this new black hole was discovered. We got a duplicate signal of a rare gamma-ray burst, which is an intense flash of light caused by the collision of two stars. And we were able to confirm that both of these signals were the same event, but that one path of light was curved so that we saw it multiple times, which is a pretty clear indicator that something with massive gravity is somewhere along the way. This new black hole is not what we would normally call supermassive. It's only about 55,000 times the mass of our Sun, which is like 1% the size of the black hole at the center of the Milky Way. But obviously that's a decent bit bigger than even the largest of stars, the missing link of black holes, so to speak. Study co-author Eric Thrain suggests that this new black hole may be an ancient relic, formed in the early universe before stars and galaxies, and those like it may have been the seed black holes for larger black holes, which now are at the center of galaxies. And finally, speaking of galactic-sized events, we have new ideas into one of the big questions which has been plaguing astrophysicists. That is to say, where is all of the dark matter? See, once we account for all of the matter in the universe which we can detect, there just isn't enough gravitational mass to hold faster spinning galaxies together. And we're not missing just a teeny amount of matter either. We only have about 1/6 of the matter which we would expect in order to stop these stars from flying off into free space. And if it were in things like black holes, we'd be able to detect it through gravitational lensing, or as I said, the wobble of stars in their orbits as they came near. Even interstellar gas, which actually far outweighs the stars and planets, we can detect because of its spectroscopic data and it interacts with space probes and so on. Dark matter? We really have no clue, and every study into finding it has come up short. Some scientists have speculated that it's a sort of primordial particle formed with the Big Bang, and that when dark matter particles collide, they would annihilate to produce mundane particles and some amount of energy, a theory which is supported by a strange glow which has been detected from the center of our galaxy, where dark matter would be densest. Following this theory, dark matter could collect in the center of planets, and there could annihilate to heat the planet beyond what we would normally expect. Of course, when we make these measurements, the larger the planet, the more dark matter is going to collect, which is helpful. And it's no good to look at planets that are close to their sun, like Mercury, because the heat from the sun is far going to outstrip anything that the dark matter is doing. For that matter, even just latent energy, like from the core of our Earth, is a lot of energy that's just not going to be easy to measure compared to the dark matter collision energy. So what we need is big, long dead planets far from their stars, which have had plenty of time to cool down so that that dark matter signal is more visible when we're researching it. And as I said, as we get closer to the center of the galaxy, we would expect the dark matter to become more concentrated. So if we can measure a clear gradient in the temperature of these large, long dead planets as we approach the galactic center, it'd be strong evidence for dark matter and also for this dark matter annihilation. I mean, it's all just theory for now. And even though it would be the best direct evidence in support of dark matter to date, we wouldn't get any information about its properties, just that it exists and that apparently annihilates to create energy. Even so, we expect many telescopes already in development to be used to collect data supporting or denying this theory. So, fingers crossed for a huge breakthrough with dark matter. And as always, if you're interested in anything I mentioned, links down in the description below. And while you're down there, feel free to like, subscribe, and if you think I missed something this week, by all means, tell me about it. And until next time, see ya.